Deriving component sets from a Cartesian product. Hello everyone. Let's begin our lesson on deriving component sets from a Cartesian product. Now, in our previous lessons, we focused on the forward process, learning how to construct a Cartesian product written as a cross B by starting with two individual sets, A and B. Today, we are going to flip that logic on its head. We are going to explore the reverse process. I want you to imagine that instead of starting with the pieces, I hand you the finished product, the resulting set across B, and your task is to work backward to identify and reconstruct the original component sets. A and B, it's essentially a mathematical detective game where we deconstruct the product to find its origins. Understanding the concept. By definition, the Cartesian product, written as a cross B, is a set of ordered pairs. It is very important to remember the word ordered here because the position of each element matters. In every single pair within this set, the first element is strictly drawn from set A, and the second element is strictly drawn from set B. To put this into a more formal mathematical language, if we say that the ordered pair x, y is an element of a cross B, then it must be true that x is an element of A, and y is an element of B. This mathematical rule is the foundation of our entire process. Because of this rule, we can see that to retrieve our original sets, we don't need any complex formulas. We simply need to deconstruct the ordered pairs. To find set A, we just collect all the unique first elements from the pairs. To find set B, we collect all the unique second elements. Now that we've established that we are moving from the construction of a product to its reverse, let's look at the core concept that makes this possible. In the next slide, I will walk you through a specific, step-by-step procedure to ensure you perform this deconstruction accurately every time. Step-by-step procedure. Now that we understand the underlying concept of how ordered pairs are constructed, let's break this down into a clear, actionable process. If you are presented with a Cartesian product and asked to find the original sets, you can follow this four-step procedure. First, let's look at step 1, which is to identify the first elements. To do this, you'll want to scan through every single ordered pair within the set of times B. Your goal here is to simply pick out the first element from every pair and gather them together. This initial collection will serve as the foundation for what will eventually become set A. Next, in step 2, we need to refine that collection by removing duplicates for set A. It is a fundamental rule in mathematics that a set cannot contain the same element more than once. So, if you see the same number or symbol appearing multiple times in your list, go ahead and cross out the repeats. Once you are left with only the unique values, you have successfully derived set A. Moving on to step 3, we perform a similar action for the second component, identifying the second elements. You will go back through the set of times B once more, but this time, your focus shifts. Instead of looking at the first position, you will collect the second element from every ordered pair. This collection forms the basis for set B. Finally, in step 4, we apply the same rule of uniqueness to find the final set. Just as we did with the first set, you must remove any repeating values from your collection of second elements. Once you have stripped away the duplicates, the resulting set of unique second elements is your set B. By following these steps, you'll be able to deconstruct any Cartesian product, a technique we are about to see in action with some concrete examples in the next slide. Illustrative examples. Now that we have understood the theory and the step-by-step procedure, let's put it into practice with some concrete examples. First, let's look at a purely mathematical example. Suppose we are presented with a Cartesian product, which we can call a cross B, and it contains the following ordered pairs: 1, a 1, b, 2, a, and 2, b. To find our original sets, we'll follow the steps we just discussed. First, let's extract all the first elements from these pairs. Looking at the list, we see the numbers 1, 1, 2, and 2. Now, remembering our rule about uniqueness, we must remove the duplicates. This leaves us with the set A, which is simply the set containing 1 and 2. Next, let's look at the second elements of each pair. we have a B, A, and B. Again, after removing the repeats, we are left with set B, which is the set containing A and B. So, our final result is that set A equals the set containing 1 and 2, and set B equals the set containing A and B. To show you how this works outside of a textbook, let's look at a real-world application. Imagine you are at a restaurant that offers combo meals. Each combo consists of 1 drink and 1 snack. We can represent the set of all possible combinations, let's call it set C, as a Cartesian product. The available combos are tea and cookie, tea and brownie, coffee and cookie, and coffee and brownie. Let's derive the original menus using the same process. First, let's identify the first elements, which in this case represent the drinks. We see tea, tea, coffee, and coffee. By removing the duplicates, we find that the drink menu, or set A, is the set containing tea and coffee. Now let's look at the second elements, which are the snacks. We have cookie, cookie, and brownie. Once we remove the duplicates, we find that the snack menu, or set B, is the set containing cookie and brownie. As you can see, the original menus were simply a set of drinks and a set of snacks. This demonstrates that the process of deconstructing the product is the same, whether we are working with abstract numbers or everyday items. Now, before we wrap up, let's look at some common pitfalls to watch out for. Common mistakes to avoid. First, watch out for swapping the sets. It is a very common mistake to confuse set A with set B. To avoid this, always remind yourself that the order in the notation matters. The first element of every pair belongs strictly to the first set mentioned in the product, which is set A, and the second element belongs to the second set, which is set B. If you swap them, you've essentially reversed the entire relationship. Second, be careful not to include duplicates. When you are collecting elements from the pairs, you might see the same number or letter appearing multiple times, as we saw in our first example with the numbers 1 and 2. A common error is to list the elements exactly as they appear, writing something like set A equals 1, 1, 2, 2. Remember, by the very definition of a set, every element must be unique. Once you've identified the elements, make sure you clean up your list so that each value appears only once. Finally, don't ignore the possibility of the empty set. If you are presented with a Cartesian product that is an empty set, represented by the symbol phi, don't be confused. This simply implies that at least one of your original component sets, either set A or set B, must have been an empty set to begin with. Now that we have seen how to successfully deconstruct these pairs in our examples, I want to pause and discuss some common pitfalls. Even when you understand the method, it is very easy to make small errors that lead to incorrect answers. Keep these 3 points in mind, and you'll be well prepared for our final summary. Key takeaways. First, remember that set A, which is our first component, is simply the collection of all the first coordinates you find in every ordered pair within the product, A times B. Similarly, set B, our second component, is formed by collecting all the second coordinates from those same ordered pairs. Next, a very important rule regarding uniqueness. When you are writing down your final sets, always ensure that your derived sets A and B contain only unique elements. As we discussed in our step-by-step procedure, you must remove any duplicates to follow proper set notation. Finally, never forget that order matters. The position of an element within the ordered pair is critical. It strictly determines whether that element belongs to the first component set or the second. To wrap up our lesson today, let's quickly recap the key takeaways to ensure you have a solid grasp of how to derive component sets. If you keep these 4 points in mind, you'll be able to deconstruct any Cartesian product with confidence. Great job today!